So we have 20 or 21 energy efficiency consultants with Eversource across the state of Massachusetts. And one of the very good ones that we have, a number of them are in the room today. But Roshan Bhakta is going to facilitate this new construction panel, which is the primary area that he works in. Roshan Bhakta from Eversource.
Thanks, John. Hi, everybody. So if you're on the new construction panel, I invite you to come up and find your seat right now. In lieu of reading everyone's resume off the piece of paper here, which you have in front of you, I've decided to take a few minutes to sort of frame this discussion. There's been a little bit of East Coast, West Coast jockeying here today, I've noticed, and I appreciate John pointing to the scoreboard. Yeah, Massachusetts is ranked #1 by AEC. California is certainly nipping at our heels, and there's a sense of inevitability there, I would say. The DOER, the leaders here in this room, we like to be ranked #1, and one of those areas, John actually had it on a slide, that we get ranked is building codes, and that's one of the areas that California is actually beating us in, I believe. I'm not an ACEE expert. So our state government here has been ratcheting codes rapidly, if you haven't noticed, or are not working in the construction market here in Massachusetts, and they plan on changing it again this year, maybe. That means that, yes, you can roll out of bed and design a LEED silver building, but that might not comply with energy code here in the state of Massachusetts. That's forcing design teams to do something really scary, which is think about the design. Admittedly terrifying prospect. And doing that, they need to engage with the utilities early on, think about their designs. Here at the utility, we're using energy code as our baseline, so as this code ratchets farther and farther up, the blood we can squeeze from that rock becomes smaller and smaller. So I'm excited to introduce this next panel because it's a representation of 3 great projects that are doing all of these things. They've engaged with our programs, and they're really thinking hard about their designs and thinking hard about energy efficiency within their designs. So over here to my left, we have Travis Wanat from MIT, Betsy Isenstein from Tufts, Stephen Spear from Northeastern, and Barry Shield from Payette. So please join me in welcoming our panel.
Thank you very much, Rich. Pleasure to be here. Starting to think that I felt a little out of place as I was listening to all these great presentations early this morning. And as I was hearing about their strategies and goals to get their air change rates down from 8 and 12, and I'm thinking to myself, gosh, I'm gonna get some thrown at me. We're trying to get ours down to 100, and we think that's great. And that'll make more sense as I go along in the project in the slideshow here. So you have 15 minutes, and I do have a lot of slides, so I'll try to go as quickly as possible. So I'm going to talk a little bit about the building design and the integration into the campus, which is an important tie to the program. Talk about the program development, the benchmarks, trying to find good benchmarks for what we're building, and talk about the performance and flexibility and efficiency, trying to balance all those out with the requirements for the research. And if I get to the site selection and construction, it's interesting, but I may not get there, so I'm going to try this one more time. Is it this one? There you go. Awesome. All right, so just to start off, the design and the campus integration. Huge team of designers, consultants, engineering firms. I felt compelled to put that up there. A lot of the information today was provided by Wilson Architects, BR+A Engineering, and a host of others. So I thought it was important to put that list up there. Abby Gregg also played a big role in the very early stages of the program development. Quick overview of the schedule. We started our feasibility study in 2010, and that was provided by Abby Gregg. 2012, moved into the real programming and design, and 2014 started the enabling phase to get the campus ready for infrastructure to support the building. In 2015, we started the construction, and 2018 we hope to have our occupancy. We will have our occupancy. And then there'll be another phase of the actual tool fit out. I don't think I even described the project, I'm sorry. So it's the nanoscale research is the primary function of the building. And there is a large amount of clean room that's associated with that program, so it's very energy driven. Exhaust is a common theme here, which is one of the things that we're focusing on. This is a quick breakdown of the gross and net square footages to give you a snapshot of the size of the clean room space in terms of the program. And it's a considerable amount, about 33% of clean room and mechanical space. So it's basically a machine covered in a box. So there's not a whole lot of architecture, but Wilson did a great job of trying to integrate as much as they could. We pushed back as much as possible. And that's just a little segment of the pie to show what piece of that 50,000 plus square feet is actual under filter space. So it's a tremendous amount of clean room space. And this was a program that was right-sized a couple of times, and we felt like this was the most efficient square footage to handle the program that we think we're going to be able to integrate in 2018. Here is just a snapshot of the campus to give you an idea of where we are. We're right in the heart of campus. And if I can get down to the construction side, you'll see the difficulties of that in terms of construction. But nobody cares about that. They wanted it in the middle of the campus because they wanted to have all of their groups and all of their labs and centers as close as possible because it's a shared use facility and there'll be multiple users. So getting it as close to the middle as possible was important. This is a good slide to show you all those groups: physics, chemistry, aero-astro, mechanical engineering. Everybody's going to be using this building, so having it in the heart of campus was crucial. I just put a few slides up here to show you some of the renderings, just to give you a sense of the design piece. I felt compelled to do that. This is basically looking at the front of the building, so it's the northwest corner. This is in the back courtyard, looking north. It shows you some integration into the existing, this is going to work, yep, into the existing buildings here. So we're connecting to building 13, which is where they're doing a lot of the work that they'll be doing in the new building. So they'll be moving some of that over. And this is another shot of the north face of the building, showing you how tight the site is. Oops. Programming and benchmarking. This is a good slide to show you a slice of the building and distributes the program. The one sort of outlier is the chemistry, undergraduate chemistry program up on the 5th floor. They're moving out of their space in building 4, and they'll maintain about 75% of the 5th floor. But everything else is a shared use facility. This is all the clean room, and this is the high performance imaging space in the basement. So there'll be no faculty offices. It's all shared space. So the difficulty was trying to find the stakeholders to help us inform the design. All of these user groups have their own identities, and this is kind of a scary notion to sort of give up that identity and go into a shared use building. So we were fortunate to have a strong leader in Vladimir Bolovic, who led the charge and gathered people from all these different schools and different labs to contribute information into the program. It was a pretty intense task, and they stayed on board from concept all the way through design development. It was a tough situation to try to find the right tools to get them motivated to do this. So we tried a couple of different things, ultimately having workshops and bringing all the engineers and all the designers to the table at the same time, and having that input live and having quick feedback was very helpful. As a project manager, one of the things that I'm always concerned about is documentation and making sure that all these decisions that we talked about, everybody understands what they're saying and understands what they're looking at, so then when we come back a year later and they start wanting to change things, we have some way to at least reference back that we did talk about that. So that was a challenge to do it in a way that everybody felt collaborative. And then, defining the environmental criteria for research. A lot of the struggle is getting this information from the various tool manufacturers for plug loads, for temperature, and you get sort of veiled information. Everybody gets a little bit conservative. Engineers get conservative. By the time the numbers come back, you're at 4 times, 5 times what you need to be. So trying to have those tough conversations to figure out what the real load is. So we feel like we've done that. We're bumping into a few things now, but we're working through them. Flexibility. So now we're trying to look at ways to build and design the building to meet the needs for the research in the next 50 years, which is changing constantly, but also being efficient about it. So having the capacity, but being able to operate it efficiently was a struggle. So we needed to figure out ways in this benchmarking study to try to find out what are the main targets to look at. So one of the first things we did was sort of list out all of these energy conservation measures that we thought were important to try to integrate. So we came up with about 140 of them. This is all fostered with the help of BR+A. And going through that 140, we found about 60 plus that we felt really confident that we can work into the design. And also informing that was the survey that we did with all of our peer institutes across the country to try to find out what are they doing. It was difficult because everybody measures their utility, their infrastructure differently. Some don't measure it at all. So it's a matter of trying to figure out how to put some sort of algorithm in there to get down what the real load is. So one of the things we did in our analysis was break it out between 2 different categories. We called above and beyond. We used the stretch energy code as our basis. So we found a lot of ECMs that sort of fell into the requirement, but could outperform the requirements. And then we looked at as many as we could that went beyond that. And they weren't necessarily unique ideas, but we tried to combine them to make it a unique strategy. Sort of help inform that, BR+A developed this bubble chart. So you want to be in the center, which is your sort of zero cost, and the size of the bubbles is your carbon footprint, and then you have operational costs. So trying to get those ECMs in the middle as much as possible. Let's see if this works. That last slide was all of them put together. This is just a snapshot of what we call the above the energy stretch code ECMs. Fan coil loads are in here. The exhaust you'll see on the next slide as some of the beyond strategies. And the return air handling unit obviously was one of the sweet spots. Exhaust air as well. So those are some of the items that we really wanted to focus on. Same with the heat exchangers. So out of that, we picked eight targets: the exhaust heat recovery, variable air volume on the exhausted makeup, 100% filter coverage in the clean room, variable air volume for the RAHUs, for the return air handling units, clean class 100 air change rates at 165. We think we can get it down to 100. They're usually around 350 to 5, so it's a good target. Local reheat for the low temp for makeup air, and we have a subcooling chiller that's local, so we can get some heat recovery from that as well. And relaxed clean room dew point, so allowing for a lower setting. Based on all the input from these institutions and the benchmarking chart that we put together, we felt comfortable that out of the 8, we could hit 6 of those. And the last one that's in red here is still on the table. We have the ability to operate at that temperature, but we got a tremendous amount of pushback from the researchers saying that they absolutely needed that and they weren't going to budge. But we're not going to give up. We're still going to try. So we have the ability to go back and try that once the building gets populated with tools and they start their program. I thought this was a good slide to show that just sort of graphically gives you a sense of the impact of the VAV and being able to turn down on the makeup air handling units. This is the sort of the before image, and this is the after, which is basically showing that gap in the requirement for makeup air by having that ability to turn down. So it's significant. Overall, this is what we've garnered for our projected performance for building site energy consumption, which is around 29%. Baseline was 228, and our proposed is about 163,000 MMBTUs. And then correlating with that is the energy cost, which we're working at a baseline of the 3.7, and we think we can get down to 1.8, which is about 51%. So it's going to be probably about 2024, 25 before we get some really good informative data on that. 2018, when we open, we'll have a lot of the high-performance process benches and hoods installed, but no tools. So the tool installation will be about 4 to 5 years. And as far as lead goes, right now we're projecting a pretty solid gold position, and I highlighted the fact that we've achieved the 19 points under EAC 1 for the optimized energy performance, and we're basing this on the 51% energy cost savings compared to the lead baseline. So in terms of the site, just a little bit of information about that. So it's the performance requirements for the program call for very, very strict vibration and EMI mitigation. So we studied many sites around the campus that were up for grabs, and we took some measurements for vibration and EMI over the course of several days and overlaid them on some of the campus maps and to sort of pinpoint where the quietest space was. And unfortunately, it was right in the middle of campus. So I obviously don't like this slide. It gives me nightmares. But they loved it. They said it's perfect. It's right where it's supposed to be. And it's going to touch all the researchers. So at the end of the day, it was the best spot from a research and programming standpoint, not for construction. So I'll fly through these pretty quick. There's just another shot of the campus location. It looks like there's 3 ways to get into this site, but there's only 2. This one we ruled out because it's not structurally sound. So this is our main entrance into the site, which doesn't give you much of a clearance. And that's the high clearance too. So all our concrete and steel comes in that way. And here is the other entry. So you can imagine what goes through there. Yeah, not much. So logistically, obviously, is a pain. So here's the sort of another image of the impact that we've had on the main group. We basically removed 100 parking spaces, most of those for the VIPs, which that wasn't really a great thing for me to do. Put me on the radar screen. And this continues to grow. We tried to maintain our site offices inside this red area, but now we decided to put them over here in the main group parking lot. So we're over here now too. So it's great. The first year was the enabling. I just thought it was important to show the amount of utility work that we had to reorganize and add to support the building. We brought new chill water lines across Vassar Street. We upgraded the electrical. We upgraded the tel data. We upgraded the sanitary storm, fire protection, actually everything. The only thing I don't think we touched was the compressed air. That's about it. These are just images to show you. We went through and we surveyed before we went in there vertically and horizontally within like an eighth of an inch using BSI to get all the existing utilities located and then sort of weave in our new ones. So that just goes to show you the complexity of it. Oh, this is all this fun stuff we uncovered every time we put a shovel in the ground. So broken valves, abandoned lines, failing lines, things that were reconfigured incorrectly. So that all became part of our project. Then they also decided to add another building in here too. So they were going to renovate building 31. So now we're all sharing this entrance over here. So they'll be done before me. So it's actually working out pretty good, better than I thought. That's just a picture of the logistics plan. This was one of the unforeseen conditions. This is the footprint of the existing, 5 minutes, okay. the existing footprint of Building 12, which is the building we demoed to build our building. And typical lab building at MIT, we expected some mercury in some of the piping and some asbestos, like you do. We ended up uncovering mercury in the drain line system, all over the drain line system, like flowable mercury, like 150 pounds of it. So that was something that was never before seen. Yay. So it was a great opportunity for all of our teammates at EHS. They were excited about it. This is great. You know, we can write papers about this now, and I'm just like sweating. But it was amazing. The construction team, the EHS team, our internal team, everybody came together and we dealt with this. This is a 2-hour presentation, so I won't go into the detail. But it was amazing that everybody came together and was able to come up with a solution. So that was, I thought, worth mentioning. This is just a little snapshot of the demolition and give you some stats. There's the 150 pounds of mercury. Yeah. Oh yeah, that's them taking out some of the pieces of concrete. Everything had to be done under containment and wrapped and triple wrapped and taken out, so that was efficient. Chill water, this is just some snapshots of the new chill water line we brought in from across the central utility plant. It's not only going to serve our building, but it's also going to help the larger campus loop be more efficient as well. This is just a snapshot of the amount of welds that we had on that chill water pipe. Every single weld was logged, tagged, and stamped. And Turner did a great job of keeping track of all this stuff. It's good information for the utilities group and good record keeping. So this is just an example of that. This is to show you the complexity of our high voltage, 13.8 high voltage loop that we had to connect to without taking any part of the campus down, which was a challenge, but they were able to do that. So I thought this was a good slide to show about 13,000 lineal feet of conduit. Slurry wall and cap beam stats. We were already out of the ground. This was taken probably about a month and a half ago. And right now we're into steel structure. This was taken, I think, Friday. So we're about 13% complete. We think we're going to be done with the structure hopefully around May, June. And that's it. So.
Good afternoon. I have to say, after listening to your presentation, other than the mercury issue, a lot of our process followed a very similar pattern. But I'm not here today to talk about the technical aspects of our building, but more of the process that got us to designing and building a high-performance science building. So just a little bit of background. Our building is a 79,000 square foot addition, which is what you see in the rendering, a 96,000 square foot renovation, and in total it'll be a 175,000 square foot science and engineering complex that will have teaching labs and wet labs and biology and mechanical engineering offices, and also will house the civil engineering and the School of Engineering itself, and it is on track for completion the summer of 2017. So the process of getting from the idea that we needed an integrated science building to this beautiful rendering to the next slide, to this building that is starting to look like that beautiful rendering, but isn't quite there yet, is really what I want to focus on. There's a bunch of people from Tufts here today, and they might not all even know that this is the third site for this building and possibly the fourth concept. There might be more of them. It's been a long time, a lot of years in development, but obviously its time and place has finally come. And you can see from the picture that it's nestled between two existing facilities, not an easy site, same kind of site enabling work that had to be done. It was the nexus of all the utilities on that part of campus, and I always say there's a reason why no one ever built a building there before, but we've done it. And It was, it's in its original concept, it was a standalone facility. It is now hooked into another building. So it's not what we thought we were going to do from the beginning. But we did know that this science building was going to be terrifically energy intensive. And we wanted to figure out a way that we could pull this off on our campus where we didn't really feel like the energy infrastructure was equipped to handle it. So we became very focused on minimizing energy use in the building. So while the university, while the university was developing their concepts for the science that was going to happen in the building, we were working on a process to get us to high performance. And so I go to a lot of conferences like this, and the NESI conference, and all sorts of conferences. And over the years, I've listened to case studies of high performance buildings and have looked for a common thread. How did these teams get this work done? And what I saw was a really strong emphasis on building science and really amazing engineering. And then after I started looking even more carefully, I found that there were some of the same people and firms working in this space. And so my personal bucket list for Tufts was to work on a project with one of these kind of dream teams. So the team, as you saw on the MIT slide, is huge, and I probably am missing a few. And those are not the actual consultants, but those are all the various different disciplines and stakeholders that you have to pull from the university and outside the university and from the utilities and from all over the place to get it done. It's a lot of people. It's like more than a village. It's like a country. And so we really worked hard at forming this team. So we went to one of those building scientists, who some of you might know, Mark Rosenbaum, kind of known in high-performance building circles, done a little work at MIT, a little work at Dartmouth also. We were very much inspired by him. And I'm going to read to you his words, because I think this is key in any project, but especially in a high-performance project. The key aspects of the process include a collaborative team. Let's see my thing. Collaborative team with superior communication and analytical skills, a schedule that allocates more time to the conceptual and schematic design phases, so that unconventional approaches can be researched and vetted, and a decision process in which competing strategies are openly debated and informed choices are made. So that, in a nutshell, is what you have to do, and what we tried to do. So the first thing we did, which I think was a little unusual, after we hired Mark, was we hired our MEP engineers. We did that before we hired any other consultants. And we had the pair, or the team, help us pick out the rest of the design team. A little bit different, hadn't done it before. I don't know if we'll do it again, but I think it was very, very effective for this particular project. So we went through a very rigorous selection process, and we picked the rest of our team and got to work. And, whoops. And we worked hard on goals. I have to say that we maybe borrowed some goals and strategies from previous projects that were very successful. We became very, very focused on one goal, and that was EUI. We looked at buildings that were modeled. We looked at the performance of buildings that were modeled. We looked at what could possibly be done, and we settled on a very round number of 100, which is something we could all remember and work towards, and that we did. So this is, you've all probably seen kind of the tenets of getting to that high performance building, very important in the process. And in the end, we ended up with lots of strategies similar to other high performance buildings. There they go, probably can't read them. But they all come together to give us the EUI that we were looking for. So it wasn't, we had a very ideal process set out, and I think that we used quite a bit of it. Mostly we stuck to the process. Mostly we stuck to our goals. In the end, I don't think we had the time or the person power to do all the things that we had hoped to do and to participate as fully as we had hoped to. We had all sorts of visions, but we had a really, really amazing team that could backstop us. When we couldn't do it, they could. We tried very hard to focus on the very big decisions where we debated endlessly over what kind of heat recovery unit we were going to use and what kind of chilled beams we were going to use. And in the end, all the decisions got made, and the building is under construction. And right now, we're focused on trying to anticipate transition to operations and how we as a department and a university are going to get this building to operate as designed and truly achieve our EUI goals. For me.
Thank you, Betsy. I'm excited for the next team. This is the first time in history that an owner and an architect are presenting on the same project. They're going to be standing up here together, so please
I need his support.
Stephen and Barry.
And I'm just going to spend a few minutes of your time, and then I'm going to turn it over to Barry, who's the expert, really. I just wanted to say thank you to the symposium for inviting Northeastern. We're very excited to be here. It's our first time, and we're presenting our jewel of our building. It's the first academic building that we've done in more than a decade, and the university has really been concentrating more on housing and that type of project and renovations. This project is the first project of our 10-year master plan, which is located, if I could have the next slide, please, because I'm not touching that thing. All right, there we go. Which is located between the Southwest Corridor from the MBTA, Amtrak, and Keolis, and Columbus Ave. And the site was one of our last remaining parking lots, so it was an easy choice. And being located, within the rail corridor, you can imagine the complexity with dealing with three agencies, rail agencies, in trying to, build this building. But it also, it pales in comparison to building the building. But the building has been programmed for about 114 principal investigators, and it has a combined total occupancy of about 700 people, and it will support research from 4 of our colleges: the College of Science, the College of Engineering, Beauvais College of Health, College of Computer and Information Science. And if you look at the right-hand photograph or image, you'll notice that it's it's a 3D image of the building, but it also portrays a path, which is what we're calling a pedestrian walkway, which is to try to connect the campus as it goes across the tracks for the MBTA. The building is a 6-story building of approximately 235,000 square feet with seating capacity. It has an auditorium with seating capacity for 175 people, classroom spaces, teaching labs, an open glass atrium located between the science and the science portion and the supporting office space. And the overall theme of this design was just basically science on display. And with that, I really would just like to turn the program over to Barry. Barry is going to give you more of the technical aspects. I'm just the generalist. Thank you.
Thank you, Steve. Good afternoon. Let me see if I can. So this is the new building. It's under construction and scheduled to open here at the end of the year. The work underway is to try to achieve a building that's in that, again, that goal of trying to be down around 100 for an EUI. And I think right now we're tracking about 103, not quite as aggressively as where we had planned to originally. But to try to achieve those kind of savings on a building of complexity, which we all know is a real challenge. There's sort of a two-pronged approach that really has to happen. One is the technical aspects, which I think we've all been talking about and dealing with, which goes to any project, whether it's a renovation or new construction. And I think what I wanted to talk about a little bit are some of the design and programming integration issues that we brought to the development of this design, which I think has to do with working together with the program groups, and specifically being able to work with the provost of the university, the vice provost for research, and the deans of the various colleges to take and do the goal setting and to develop the program is essential to try to reach some of these goals and targets. So I was going to try to look at three aspects of that. One is about office air reuse and the building programmatic orientation. And then energy zoning of the laboratories and how that is really developed through how we approach the design of labs and what that means programmatically for the institution. The technical aspects, I think I'm going to sort of leave off to the side. We can certainly answer questions about that later. The building was designed around an atrium, which Steve mentioned. I think the atrium is kind of an essential component to a lot of the energy benefit and energy targets that we are trying to set. A lot of it is trying to take and develop a system where the air for the laboratories can also fund all the other air that's used within the facility. So we bring in air and we're trying to use it 4 times. First within the offices, all of that air then transfers to the atrium, which passively returns to the main mechanical systems of the laboratory block here on the right. At that point, the building can choose whether it's going to use that air, if that's the right air to be using, given its profile, or it can take from the outside, either from untreated air from the outside or from a preheat plenum that's doing a passive solar preheat. So it gets 3 choices to make, and then that air is brought into the facility. And when it's brought into the lab side, there's this balance between what is dry lab and what is wet lab. And that was part of this programmatic negotiation with the university and with the constituents. And delivering that air first to the sort of soft and office and dry side of the lab, and then transferring that air to that. So effectively, we've used the air 4 times before we exhaust it from the building, and that drives a lot of the strategy of the building. Another piece is the orientation, and in an existing facility, you don't get this benefit, but when you're designing a new facility, you really need to pay attention to developing what is the solar exposure versus the thermal exposure, and then working together with the programmatic layout of the building about how the offices and the low internal load profiles of the building orient to that thermal load, to that solar load, and then really allowing the high performance spaces and the ones that have the high internal load to work specifically in this climate even more benefit to be up against that sort of thermal enclosure of the building. And working together with the university, we're able to take and achieve, I think, a lot of that as well. Part of the look of the building comes with how we then take that solar exposure, which wants to have lots of nice glass and openness for the offices, and balance that with a solar shading device, which has been fine-tuned to both provide sort of the daylighting, glare control, as well as solar exposure control for all of that glass facing west. And that sort of gives us sort of overall infrastructure of fins that protect the exterior exposure. The zoning of the laboratories comes into trying to develop what I said is the dry zone or the computational zone of the lab, and working that separate from a medium energy zone, which is separated by a scrim of glass that separates the 2 zones. This allows us to take and dial down the air again further within the lab, but within the lab where chemical use is restricted. And so here's where all of the computational work happens, all the write-up happens. That can be then run at an office kind of level, and the air from that zone can then be transferred into the lab to help make up the air for the 6 air changes that is the goal in an occupied mode for the open lab. The other thing that the university has done working together with us, and I give most of the credit to the sort of leadership on the university program side is that there's a very big focus on shared facility between research groups. So it's planned as an open lab, and part of the goal was to also not only have the sort of assigned lab of the open lab, but within this higher energy zone that's sort of been laid out adjacent to that. The idea is all of the instrumentation for the project and all of the higher plug load use of the project works into a zone where there is a real focus on sharing those facilities between research groups to the point where they're actually dialing down the number of pieces of equipment that they're proposing to bring and then sort of facilitate that sharing between researchers. So I think that is where a lot of, again, it takes down sort of the overall square footage requirements of the project where you're not replicating things for other researchers. So that's sort of an overview. And then I think this was hit on a lot before as well, is that as we're doing these dialed down air scenarios for the labs, that the CFD modeling of what we do becomes more and more essential. And sort of 6 air changes is that kind of sweet spot of compliance right now by code, and meaning OSHA and all the other guidelines. But even if you're just going to say you're going to do that prescriptively, I think you really need to take a look at and confirm the compliance of the lab, that the right air change turbulence is actually happening throughout the lab and providing that protection throughout, so you don't have the sort of dead spots that I think were pretty well documented in some of the earlier presentations that were made today. So that's sort of our overview. Thank you.